Hi, my name is Paul Washburn, and I'm going to present an experimentation into predicting future crude oil prices using deep learning. Forecasting the price of crude oil has been of particular interest to businessmen and economists ever since fossil fuel transportation started. The advent of deep learning has provided a new class of models to apply to the problem of forecasting these prices. Densely connected neural networks provide a sufficiently complex class of models that may be able to tease apart the complex relationships that determine crude prices. The market price of crude oil is complex and subject to both economic and political factors. This analysis explores the possibility of predicting the future price of crude oil using deep learning. The Keras and TensorFlow libraries for Python are employed to perform a grid search cross-validation over a feed-forward neural network architecture. The hyperparameters that are varied are dropout rate, units per layer, number of layers, and regularizer lambdas. Then the best model out of 96 models is identified. Given that crude oil is a cost input into nearly every industry, accurately forecasting its price could be of great utility. Python 3 is the programming language that was used for this analysis. Keras and TensorFlow are used for the deep learning, Pandas and NumPy are used for the data cleansing, and Matplotlib is used for visualization. My machine is a Windows 10 running on a Lenovo IdeaPad 700 with an onboard NVIDIA GPU. My processor is an Intel i7, and my GPU is a GTX 950M with 4 gigs of RAM. My machine has 16 gigs of memory. The Pandas data reader library is used to access the Federal Reserve of St. Louis's FRED API. 17 economic variables on equity markets, currencies, interest rates, debt markets, commodities, and volatility in the energy sector are gathered. Calendar features such as month, weekday, year, and holiday are added to the data. Then, missing data is imputed using a simple backfill followed by a forward fill method. The goal of this analysis was to use a grid search method to build a reasonable model that could predict the price of WTI crude oil 30 days in the future. To accomplish this, the data was acquired from FRED, explored, and visualized. Then, in an attempt to smooth signal from the volatile data, features are extracted from the original data. First, percent changes are calculated, and then rolling means on those percent changes are used as features. To find a good model, a grid search is performed over 96 different models, trained at different values for the hyperparameters of regularization rate, dropout, number of units per layer, and number of layers. Then the best model is determined on a test data set. In an effort to keep the code succinct, a custom function was written to gather multiple time series vectors from the FRED API and then merge them into a single data frame. The data is gathered from 2011 through 2018. Then calendar features are generated using the pandas.tseries functions to generate all days for each year since 2011. The variables chosen are volatile, somewhat intercorrelated, and non-stationary. In an attempt to smooth signal, features are extracted from the original data. Daily percent changes are calculated, then a rolling 30-day mean is calculated from those percent changes. To align future prices with current data, the y-vector is shifted backward by 30 days. The goal in deriving features from noisy data is to smooth what signals may be present in the markets over a given time period so that relationships are detectable. Then, in order to adjust for seasonality, calendar features are generated and merged in as one-hot encoded vectors. Using these features is questionable. Here we have an overview of the feature engineering process. A split apply combine operation is utilized to acquire the rolling 30-day window mean of the percent changes in each vector. Then the y column is shifted backward by negative window periods. While the data is still in this format, it is visualized. A custom time series plotting function is used to characterize the rolling averages of the percent changes. When comparing them to the original data, nearly all of them center around 0 and look to have a somewhat normal distribution on the histogram on the right. Then a correlation matrix is produced and visualized using a heat map. This heat map shows that a lot of the intercorrelated nature of the variables still exists in the derived features. Keras is then used to define a feed-forward architecture. This model is instantiated using various hyperparameters. 96 different models in total are trained and tested. Early stopping was employed in order to make sure that the model does not overfit. To keep the code succinct, a simple function is written in order to instantiate each model. Then the grid search is performed using a simple nested for loop. As a side note, this code could definitely be optimized using something like Python. Then a model is instantiated for each permutation of the hyperparameters using early stopping. In general, the different models performed pretty well. In the background, we see the actuals versus the predictions, with the predictions on the y-axis, and we see that they align rather well. In the foreground, we see the loss function over the number of epochs trained. This model performs very well. However, it is dangerous to assume that we have a model that can predict the future price of crude oil. Here we have a plot of the final results of the predictions versus the actuals on the entire dataset. It can be seen that the predictions track relatively closely to the actual values with some error thrown in. Interestingly, the R-squared on the test set is very high at 95.4%. Here's the notebook that is used to produce the analysis covered so far. First, the Fred API is called for all the series in this list. Then, calendar data is merged into the dataset. NA values are filled using a backfill, then a forward fill. And future values are eliminated from the dataset. 100 encodings are then produced from the month, year, and weekday vectors. And the columns are made lowercase. Split apply combine was applied to the problem in order to produce the features. Here we melt the data frame on the date column so that we can perform a rolling 30-day average of the percent change, which is calculated right here. While the data is in this format, we can visualize it using this custom function. As you can see, the function produces a time series with a mean, a rolling mean of 50 periods, a rolling mean of 150 periods, and a histogram. Now remember that these vectors are rolling means of percent changes. And here we have The only one that is not included in the predictor set because this one is derived from the actual price of oil. Then the data is reshaped back into a machine learning friendly form. A correlation matrix is then generated. This should say correlation. A correlation heat map, is generated using a Pearson correlation coefficient. The zeros are muted across the diagonal, or the ones rather. And then the cutoff is used in order to mute low expression correlations. We can see that not all of the correlation is removed between the x variables. Next, the actual price of oil is mapped into the data set by date. Then we split and scale the data, and also chop off 50% of the test set as validation data. Next, we define plot loss function, which accepts a Keras history object as an argument and plots the loss. We then write a function to instantiate simple feed-forward models so that we can do it in a for loop. And grid search is performed on these variables. Early stopping is employed during training so that we do not save an overfit model. Here, only models that are greater than this cutoff, which is defined here, are printed as a plot. So here we can see that not all of them are printed. Finally, we gather all the results into a data frame. We do a quick plot to look at the R2 score over a different number of units. And we identify the best model. Here it is a 2-layer model with dropout at 0, 34 units, a regularizer parameter of 0.005, and it is able to achieve 94.5% accuracy, or R2 score rather. It is saved, and here we plot the predictions versus the actuals. This function right here is used to generate prediction-worthy x variables so that we can plot the actuals versus the predictions for the entire data set, which is produced right here. And then we plot the final results here, where we see an R squared of 95.4. It is important to note that this 95.4 changed from a previous permutation of this notebook because a seed was not set during the split part of this analysis. Some lessons learned from this analysis. Time series features such as month and weekday can be useful. However, in this instance, it seems as if they are facilitating overfitting. Autocorrelation in economic variables makes unique signal extraction difficult. Most of all, it's important to realize that this model is likely too good to be true. In order to refine it more, real-world testing will be necessary with no stakes. Some future work ideas. Firstly, testing the model in the days and weeks to come would be a good idea and a great place to start. Testing the model under different rolling average values such as 60 days and 90 days may also be helpful. The architecture of the model could be changed, or an LSTM, GRU, or reinforcement learning techniques could be used. Since little literature was reviewed for this project, the literature on state-of-the-art practices in forecasting crude prices could be visited much more deeply. Finally, other predictors could be explored, such as OPEC information and political aspects in the oil market.